Hey guys, this is Sandeep. In this video, let's see how to make a plutonic solid, the regular octahedron. So without any further ado, let's get started. First, cut this paper into two pieces. Okay, now that we have a single half, let's bend it into two. Okay, now Now what you do is you take a single piece and make it meet the middle line, midline. So I'll just take this. And you continue the same with the other side as well. Take the other side.
Oh. See, now we've got the octahedron.
Hi, welcome back. Now that we've made our origamis, that is, the regular octahedrons, let's just verify the famous theorem quoted by Euler. First, I'll tell you what's the theorem. The theorem states that in any geometrical solid, there is a definite relationship between number of vertical edges and faces. Now, let the edges be E and the verticals be A, B, and let the faces be F. Okay, now the theorem states that F, that is the number of faces, plus V, that is the number of vertical, is equal to 2 plus the number of edges. This is the famous Euler's theorem. Now let's verify it for our octahedron. I'll take the octahedron in my hand. Okay, let me just keep one. Let's count the number of faces first. 1, 2, 3, 4, 5, 6, 7 and 8. So the number of faces in an octahedron is 8. This oct, right? So number of faces is equal to 8. Next, let me count the number of verticals. 1, 2, 3, 4, 5 and 6. So it is 6. I'll bring this 2 down. And next, let's count the number of edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So it is 12. Now LHS is equal to RHS, right? 8 plus 6 is nothing but 14. That is equal to 2 plus 12 is nothing but 14. Thus, we have verified our theorem. That is, F plus V is equal to 2 plus E. This holds for any geometric solids. You see, right, we've derived a mathematical expression from the shape we have, and we have also verified it. This is interesting, right? Yeah, that's it about octahedron. So, hello all again. In this video, let's see how to make a hexahedron. See, normally if I tell hexahedron, what do you all know? It's cube, right? But there's an other form of hexahedron which I'm going to make in this video. I just need a square paper for it, and then bend it like this. Next, like this. Next, this, like this. Next, take this and bend it like this. You got it right. Next, just bend it like this. Now, if I open and see, it will be some structure like this. Okay, so you're requested to make 3 of this so that we can build a hexahedron model from this. This is the first thing, and I'll just make other 2 in the similar manner. I'll take a square piece of paper. I'll just bend it like this. Next, like this. Next, like this. Next, and the final part is like this. So I have a similar structure, and I'll make another one. Which will look like this. Now we'll start building a model. First, I'll take this brown one and I insert pink one at this corners. I'll insert it like this. You see it, right? I'll just tuck in a little bit. Now it's perfectly fine. It looks like this. Now I'll take this part and put it inside this thing. You just put in here. One minute. just put this thing in. And let's tuck in further. Now you get something which looks like this. Right. I'll take this red thing and put it inside this. That's perfect. And I'll just put this thing in like this so that it's locked perfectly. See now, you see the magic, right? We've got a hexahedron. See, first you'll think this is a tetrahedron, but actually this is a hexahedron model. In this hexahedron there are 6 phases. 1, 2, 3, 4, 5 and 6. And now we have a different form of hexahedron model ready. Note that it's not a regular cube. This is a different model, but it's a form of hexahedron. Now let's go on and verify Euler's theorem for it. What does Euler's theorem state? Let me take the number of faces as f and number of verticals as v and the number of edges as E. The Euler's theorem should satisfy for it, right? First, let me count the number of faces. First, before that, even the name suggests it's a hexahedron. What does hex mean? It means 6. So there should be 6 faces. We'll verify it. 1, 2, 3, 4, 5 and 6. So the number of faces 6. And now let's count the number of verticals. 1, 2, 3, 4, 5. I'll re-verify it. 1, 2, 3, 4 and 5. Now let's count the number of edges. 1, 2, 3, 4, 5, 6, 7, 8 and 9. So the number of edges is 9. So what does the Euler's thing state? F plus V is equal to 2 plus E for any the 3D solids. So 6 plus 5 is equal to 2 plus E. What is E? 9. So 11 is equal to 11. So it's true. So the regular hexahedron that is the cube also follows the same thing, and our hexahedron we have verified it for it. So the theorem is verified. So that's it. Thank you so much.